Hello and welcome to Inside Exercise. I just had a great chat with David Wasserman from Vanderbilt University, a legend in glucose metabolism. We focused on the liver mainly. We covered all sorts of things, the glucose metabolism at rest, during exercise, what happens with insulin resistance, how exercise improves insulin sensitivity, again focusing on the liver, and also had a really nice chat about his late father, Karlman Wasserman, who was a legend of exercise physiology as well, especially with anaerobic threshold. So enjoy. So, hey Dave, how are you?
I'm doing well. And how are things down under, Glenn?
Oh, pretty good, pretty good. It's a bit cold. Hey, so anyway, we're talking about the liver today, yeah? So what do we care about the liver? This is an exercise podcast. Like, what do we care about the liver?
The livers can be difficult to describe because we know the heart pumps, the muscles contract, the vessels dilate, but the liver does a little bit of everything. And it is absolutely essential if we're going to exercise for more than just a few minutes. So the liver is a battery. It's a rechargeable battery at that. It releases energy when we're under stress, when our energy expenditure is high. And when we eat, it recharges. The liver is a recycler, okay? And it was a recycler before recycling was popular. And the liver detoxifies. So it takes nitrogenous compounds during exercise. And of course, it's a detoxifier for many, many compounds, pharmacological agents, as well as things we produce endogenously. But with exercise, it's particularly significant that it takes nitrogenous compounds and it'll scavenge the carbons and turn it back into glucose and then make urea from the nitrogen that it gets.
Wow, okay.
All right. So the liver does everything.
There's a lot of stuff there. So we're going to unpack that. How about we step right back? So as you said, the liver is doing tons of things. I read like 500 different jobs it does. So how about we just think, we're going to focus on metabolism here, right? So it does all sorts of things, but let's focus on metabolism. So if we just think at rest, so I don't know, if you haven't eaten for a while, what's it doing in terms of metabolism, and then compared to when you have a meal and that, and then we'll get into exercise and things like that.
Okay, so in the liver, when you're in what would be a post-absorptive state, that is a fasted state, the liver is the source of glucose for the body. And it provides glucose for all the tissues. The brain, when we're not exercising, is the primary site of disposal. It takes care of about 60% of the glucose. And that changes dramatically when we exercise. So the muscle becomes the main site of glucose consumption.
Yeah.
Now, when we eat, the liver switches its role. So I've talked about the liver being a rechargeable battery. Eating is the recharger. And the food that comes in through our GI tract pours into the gut and into the portal circulation and is taken up by the liver. Some is stored as glycogen. Others go in and carbons are oxidized, or if they're fatty acids, they can be metabolized in other ways. Lipoproteins, triglycerides, the whole.
Yeah, so there's a lot going on. Yeah, so just if we step back then, just at rest, what are the hormones doing? So, people know if we're talking about glucose, we're talking about, insulin and other hormones. Now, you've done years and years of study. I mean, why don't we just step back a bit? I mean, how long have you actually been working on the liver?
I think since the early 80s. I hate to admit that.
But and you've been at Vanderbilt the whole time, yeah? Since you started?
Well, I started studying the liver with Mladen Vranic, my PhD supervisor in Toronto in 81. I moved to Toronto, to Nashville rather, in 85, and I've been here ever since.
Wow.
And so, yeah.
amazing studies. Everyone knows David Wasserman. So to understanding glucose metabolism, yeah. So what's the glucose doing? How much glucose is being released from the liver? What's been taken up during exercise? How it's regulated? He did all those amazing studies in chronically catheterized dogs, which people tend to get a little bit concerned about, which is which then you've moved more to mice studies. So, but just if we step back, and you've done. Why don't you tell me? Why don't you tell me what models you've used over the years? Yeah.
Well, to tell you the truth, I've probably I've studied. I've actually had a few studies in humans, rats, mice, and dogs, and each model has a specific purpose and offers specific benefits. So sometimes you run into these people who become real advocates for a particular model system. But in fact, the thing I learned is that you need them all. You need to have to be able to translate to humans, obviously. I mean, that's really where the impact is. The dog studies were really important in that was the only way that we could get access to the portal vein that perfuses the liver. So to be able to sample from that obscure vessel, perhaps obscure is not the right word. The liver thinks it's very important. But in terms of access, it's not accessible in humans. It's you can access it in rats, but you can't. You don't have the blood volume to make the measurements you want. We can catheterize it in mice, but again, you have the blood volume issue, and it's better for infusions than it is for sampling for that reason. So I've worked in a number of model systems, and I think I learned a great deal from each one. And the occasional debates about the importance or the value of working in large animals versus small animals versus we need them all. Yeah. They each have their own intrinsic value, and so I think that is really why I've ended up covering the spectrum. Now, our lab now has been exclusively mouse for the last 25 years or so, and so you know, this is really where we've settled, primarily because we have some really nice tools that allow us to address questions in mice that might not otherwise be doable. So I've always had very skilled people to keep me out of trouble, and I have a good crew for studying the mouse.
Well, that's how you've been able to really, you know, clarify for us what's happening to glucose metabolism at rest and during exercise, and also with insulin resistance. So we'll get into that more. So just to give a bit of an overview, so is it fair to say that during at rest, you know, insulin increases after a meal, and that's an important factor for storing the glucose? And then during exercise, what happens for insulin, for example?
Well, exercise is interesting. Insulin falls with exercise, and the amount it falls depends on may depend on the intensity of exercise, the duration, the prevailing blood sugar, the nutritional state. But it's safe to say that in general the insulin falls, and that's an important thing, because the fall in insulin inhibits glucose production from the liver. When insulin falls, the liver is more able to produce glucose. So the decline in insulin is critical for the mobilization of glucose from the liver. On the other hand, at a first glance, it seems paradoxical that the muscle takes up more glucose in the face of less insulin. But what we now know is that the glucose uptake in a contracting muscle is insulin independent. And I imagine you need a requisite amount of insulin just to keep the body under control, to keep lipids in order, and just for basic housekeeping. But the contracting muscle can consume glucose in the absence of insulin.
Exactly. So you did those pioneering studies there, looking at, you know, what's happening when you start exercise. There's a decrease in insulin, increase in glucagon, adrenaline. You want to flesh that out a little bit, and even maybe touch on the fact that if you're doing intense exercise, you know, the glucose can actually increase in the blood rather than just being sort of maintained.
Right. So the full hormonal picture is complex, and those have been delineated by many people in the lab, including Henrik Galbo in the 70s, and in Copenhagen, and other people who've come along since then. Now, what I've been interested in, and I think that these really are the main acute regulators of liver function, is that you have a fall in insulin with the onset of exercise, but you also have a rise in glucagon. And those two things increase glucose production and allow glucose to go out and meet the needs of the working muscle. Now, I want to clarify something, because if you're to measure glucagon in the systemic circulation, you won't necessarily see a rise in glucagon until maybe 30 minutes in to exercise. So the important thing is what levels is the liver seeing? What are the glucagon levels at the liver? And the body is designed in a very efficient way, so that the pancreatic hormone secretions directly hit the liver. They drain the pancreatic vein, and they go into the portal circulation and hit the liver right off. That's really efficient because it allows high glucagon levels to occur without creating this large wasteful systemic glucagon, without having to fill up the extracellular pool. But as efficient as it is for the body to work this way, it's an experimental nightmare. So the experimenter cannot directly see what glucagon levels are at the liver. And this is where the studies in the dog were important. And unless one wanted to argue species differences, which you can never rule out, is that the glucagon levels go up immediately and to a marked extent with the onset of exercise, but the liver filters so much of the glucagon that all you see coming out into the systemic circulation are low levels of glucagon, and they can be undetectable until you're partway in. Now, these same, we think this applies to humans, and I think there's actually a fair bit of data now that's saying glucagon and insulin, in fact, are the main controllers. The rise in glucagon, the decrease in insulin. And what we know from studies from Michael Kier and Bob Wolf, Phil Cryer, and Carol Lavoie, is that if you prevent changes in glucagon insulin using a pancreatic clamp, blood glucose will fall. Now, what Phil Cryer and Carol Lavoie showed specifically are that the changes, and keep in mind they're inducing these changes with a systemic infusion. They've delineated specific roles for glucagon and insulin. So the caveat with human studies is that you're delivering the hormones via the portal vein, via the systemic circulation, whereas it typically enters via the portal vein, and it directly hits the liver.
That's very important points, because as you said, most of us, when we did our studies, we'd just be measuring from a vein, just an antecubital vein, and we'd be saying, oh, glucagon didn't do anything until 30 minutes into exercise or whatever. And but insulin you could pick up, so you say, okay, well, the glucagon is not important, it's the insulin. But as you say, we're actually not measuring where the action is.
That's correct. And the difference between portal vein and systemic vein glucagon is substantial when glucagon secretion is increased. So the liver almost seems to work like a low-pass filter for certain hormones, amino acids, glycerol. Things can enter the liver at a very high level, but they come out at a very low level. And so my belief is that glucagon and insulin together are the key controllers of hepatic glucose production.
Right, so we've talked about more sort of prolonged exercise, where you've got a situation where the liver's releasing glucose at about the same rate that the muscle's taking up the glucose. So you actually don't see much of a change, right? And again, that's an interesting one, because again, people might say, well, nothing's going on. But if you use tracers and things, you can see there's a whole bunch of glucose being released from the liver. It's pretty equal, taken up by the muscle, so it doesn't change. But then, after an hour or so, it'll start to drop, unless you have something to eat. We'll get back to that. But what about if you do intense exercise? The glucose can actually increase, which is, sort of surprises people, actually. What's going on there?
Yeah, that's a good question. When you get to a certain work rate, glucose levels increase, and the severity of the intensity will determine how high the glucose will rise. I believe that the work rate where glucose actually begins to increase is going to be roughly at around what is referred to as the anaerobic or lactate threshold. And I think beyond that point, you start seeing an increase in glucose, and it becomes more of a Walter B. Cannon type stress. So Walter B. Cannon won the Nobel Prize in 1936, I believe, for describing a stress response. And I think when you get above what we might consider moderate intensity exercise, we get that stress response, glucose goes up. Now, what controls that? And flux studies show that, of course, you have the increase in glucose production and an increase in glucose utilization. I have not, there will be people that disagree with me, but I think that there's very little indication that the catecholamines are actually controlling glucose production, even during high intensity exercise. So blockers do not have an effect on glucose production in healthy subjects in terms of curtailing glucose production.
Is this like beta blockers, so blocking the...
Oh, blocking the adrenergic receptors. Now, there is an effect. The catecholamines are very important, but it's my belief that their main role is supporting liver function by mobilizing substrates from the extrahepatic, from the other tissues of the body. So it mobilizes fat. It mobilizes amino acids from muscle and GI tissue. But in terms of direct effects on the liver, I'm hard pressed to think of really solid evidence.
What about, given I did my PhD with Mark Hargraves, I can't help mentioning, they did those studies where they infused adrenaline during exercise. I think it was Mark Fabrera, Matt Watt. They did exercise at 40% of VO2 max, and they looked at the adrenaline and the glucose output from the liver, et cetera. And then they did 80% VO2 max, and then they did 40%, and they infused adrenaline to bring it up to the same level as the 80%. And that did increase the liver glucose output, but not as much as the exercise. So what do you think? I guess there's a whole bunch going on there. But
there's a lot going on, and catecholamines are undeniably important metabolic regulators, but it's been my impression from being able to look directly at inflow and outflow from the liver that its effects on the liver are indirect.
Okay.
Now, there is one other piece of information that we know, and that is that the gut extracts about 30% of the catecholamines that perfuse it. And the gut is in series with the liver. So the liver levels of catecholamines are going to be about 30% lower than what we're measuring.
Okay. Okay. All right. Well, that's interesting. I did not know that. So I think we tend to all say, oh, that, you know, glucose goes up in the blood because of the adrenaline and whatever, but it's more complicated.
No, I think that would be wrong.
They say it's more complicated, not wrong, but yeah, it was probably wrong. Okay.
Right. Well, that's right.
That's fine.
It's more complicated. That would be the most accurate way of saying it.
So you mentioned anaerobic threshold and lactate threshold before. You know, your father was Karlman Wasserman. You know, that's amazing. What was it like being brought up with that legend?
Well, you know, as a kid, I didn't actually know he was a legend, and he was just my dad. And I was lucky enough to have a father who was a big influence in my life. It's interesting though, because I imagine that most of the people who are watching this, who know him for his research in exercise, but but myself, the family, we think of him, you know, he's father, and I think professionally we think of him primarily as a healthcare provider. And of course, we know that he is an accomplished researcher. He published papers over a period of over, you know, a span of over 70 years, I think. First paper came out in the late 40s. So certainly we knew that, and I in particular knew that as I got older. But you know, the more significant, the more dominant role we saw him in was as a healthcare provider. So he was a professor at UCLA, but he also was a physician for the county of Los Angeles. And he was very passionate about administering healthcare. You know, being a physician for the county of LA, he found it very, I think he found it very rewarding. He'd come home and talk about the patients that he saw, and a lot of his procedures, none of which were related to exercise or the things we know him from, gained national attention. And he passed away in June of 2020. And I had the responsibility of going through his old correspondences, and I really gained an appreciation of how this doctor for LA County was an international resource for so many doctors in the field. He really he was really respected in that regard. I could give you, Glenn, an entire podcast on stories about my dad and giving patient care. And he heard every "Is there a doctor in the house" page ever made. He probably could hear one in the place next door. But he always responded to those things. And I saw him administer healthcare, save lives with a Swiss Army knife and a straw. How about that? Without elaborating into more detail.
That's amazing.
Creative.
You told me that story earlier. So basically someone was choking, your father heard is there a doctor in the house, even though you guys didn't even hear it?
Nobody else heard it, but he has the little bat ears, and he picks up these things, and he responded to that. We were out for somebody's birthday. I was college age. I was in college, and he responded, and I watched from the window, and he had a little Swiss Army knife he carried on his keychain before TSA was a thing. And he gave her a tracheostomy. And then in the absence of anything else, he then took a straw and put it down the trach. And then the ambulance arrived sometime later, and he rode with the ambulance. We met him in the emergency room, and he was just so pleased when the doctor said, "That was the best incision on a trach I've ever seen." Oh. And so things like that were exciting to him. Wow. That's not to say he didn't. He was equally enthusiastic about his research, and but even his research, starting with when he moved to work with Comro in the 60s, was about developing a diagnostic tool for heart patients. So it's always been very clinically oriented and very translational.
So it's definitely.
So to answer your question, it was just fine. I think speaking for my mother and my 3 siblings, he was a pretty good dad.
Oh, sounds like it. No, I think it's a greatly simplified to say he was, the anaerobic threshold man. Obviously, there's a lot more to him than that. So, yeah. Okay, to bring it back to the exercise metabolism and sort of a bit of a segue, if we're talking about anaerobic threshold, we're talking about lactate. So if we think about, another role of the liver, which is very, very important generally, but during exercise is gluconeogenesis. So genesis of new glucose during exercise. So, and bringing it back to lactate. So one of the substrates is lactate. Maybe just flesh that out a bit. What's going on with gluconeogenesis during exercise, and why is it necessary? Because the liver starts to run low on glycogen, etc.
Yeah, I mean the role of gluconeogenesis increases with the duration of exercise. So in a well-fed person, they have liver glycogen, and they also make about 20% of their glucose from new carbons, from non-glucose carbons like lactate, some amino acids, pyruvate, glycerol. And as glycogen levels deplete with exercise or during a fast, gluconeogenesis becomes more and more important. And the important thing about exercise is the body transitions into a gluconeogenic mode. So experimentally, you can create the hormonal environment you see with exercise and not have an increase in gluconeogenesis. It's only during exercise where you have lipids being mobilized from other tissues, lactate, pyruvate coming from skeletal muscle. The gut dumps amino acids into the portal circulation. That sustains gluconeogenesis. So the hormones turn on the process, but you need to have the substrate mobilized to actually see glucose production from gluconeogenesis.
Okay. So, yep. So during exercise, if we think about just a normally fed state, so if you haven't fasted for 3 days or something, you just go and exercise. Is it fair to say probably the first hour or so, it's mainly glycogenolysis, so breaking down glycogen from the liver, and then the gluconeogenesis sort of cranks up, and after about an hour, does it start to dominate? Is that a fair sort of?
Yeah, there are so many
variables,
caveats, variables. So the intensity of exercise and how fast you go through the liver glycogen, how high your liver glycogen is when you start. But it is accurate to say that with increasing exercise duration, maybe if you were, let's say, you start off with a high glycogen level in your liver, then I think by about 50 minutes or so, if you exercise at about 50% of your max VO2, you'll be, after about 50 minutes, you'll be mainly gluconeogenic.
Yeah, and it's good to point out it's a very simplistic question, because it's going to depend, as you say, on the intensity, the duration, but even the fitness level. So if you're a well-trained endurance person, you tend to use less glucose, less glycogen, and more fat. So I assume that then, naturally your liver glycogen would run out at a slower rate, and you'd need to crank up your gluconeogenesis later on.
Yeah. I mean, one of the key factors that determine endurance is how well you can preserve your your glycogen levels.
Yes. And
athletes, one of the adaptations is the ability to conserve. And there are numerous ways they can do that. One way is by increasing the ability to use fats. So they might develop more mitochondria. They might have better blood flow to the muscle, allowing them to have increased reliance on bloodborne lipid substrates, bloodborne substrates just altogether. But primarily, the main feature is that fatty acids are a more efficient substrate during long duration exercise. Okay, you get more ATP per stored carbon.
So tell me, how does the liver actually know you're exercising? Because you said before you can manipulate hormones and you won't necessarily get. It's a complicated question, I'm sure. But how does the liver actually know you're exercising and then start pumping out glucose?
That's a really good question, Glenn, and I wish I knew the answer. I tried for a really long time, did numerous experiments to try to delineate what causes the liver to respond to exercise. I could be more accurate. I'm a believer in the pancreas, and that the pancreas stimulates the liver. My question would be, what tells the pancreas to change its hormone secretion? And initially I started with the assumption that it was under feedback control. So, the liver senses a drop in glucose, or the muscle utilizing glucose, or the pancreas changes the pancreatic hormone secretion, stimulates the liver. But I've done experiments in different species, and Michael Kier, of course, worked very much in this area as well in the 70s and 80s. And I'm not convinced I know that. And maybe the most compelling evidence actually comes from studies in the mouse. And but to tell you the truth, I haven't found anything compelling, and I don't have an answer from any species I study. But we can knock out the GLUT4 transporter, prevent the exercise-induced increase in glucose uptake, and we'll still get glucose release from the liver, to the point that the glucagon and insulin levels go up, or glucagon goes up, insulin goes down, and the animal will get hyperglycemic. So even though we've taken out what I thought was the cue for increased glucose production, that is glucose uptake by the muscle and a feedback mechanism, glucose uptake by the muscle was not necessary for the increase in glucose production. And we've done other studies in large animals that also make it difficult to provide a feedback mechanism for glucose. So the answer then becomes, or the question then becomes, what role do feed-forward mechanisms have coming from the brain? And I started off with a strong bias against feed-forward, but now I think that may be the explanation, is that the brain exercise is a conscious, voluntary thing, and when you say, I'm going to go run, a signal emanates that ignites a number of processes.
Okay, so it's like central command that we talk about with cardiovascular, respiratory. But you mentioned Michael Care earlier. He did those classic studies where he actually cut the nerves going from the brain to the liver, and I thought he got no real effect.
Yes, right.
Output.
Yeah, I don't think you'll get a response by denervating the liver. And I believe Michael, in the studies you're talking about, was using patients with, but he also did studies. Dr. Vissink, who works in Copenhagen, also did many of the studies along those lines. He worked with Jerry Mitchell in Dallas as well.
This is the thing where it gets so confusing, because my takeaway from all of those incredible studies where, you know, you also did epidurals and all sorts of things in humans,
yeah,
was that it's a redundancy. Yeah, so if you block one thing, you'll still get normal glucose output. If you block the other thing, you'll get normal glucose output. It makes it very frustrating trying to do the research and get an answer. But is that yeah?
I think that's really a big problem at trying to pick apart the autonomic nervous system and sympathetic innervation, is the redundancy of the system. And it's hard to distinguish between what's redundant and what's just altogether a different mechanism. And you know, I don't know, even after all of the great work that's been done from, in particular, the guys in Scandinavia, but other groups as well, is I think it's really a difficult question to answer. And I think this is probably a mystery that extends to other systems as well, not just glucoregulation, but what in fact makes our lungs expand when we exercise. And
that just shows, I mean, you know, the more and more we go, the more we know, the more we realize it's just everything is so integrative. There's so much going on that to try and look at one thing. So, you know, so think about what's going on during exercise. You know, you've got decrease in insulin, you've got an increase in glucagon, you've got maybe an increase in adrenaline, depending on the intensity. You're going to have a decrease in blood flow. I don't know if that gets sensed. You've got messages from the brain. You've also got IL-6 being released from the muscle, which has been suggested may affect glucose output. And also you've got, you and others have shown activation of AMP kinase even in the liver during exercise. So
yeah, I mean, there is definitely a lot of going on, and I think there are direct roles at the liver, and then there are also indirect signals that set the tone for how the liver is going to respond. So, for example, there have been publications out, a number of them, some from my colleague at Vanderbilt, Alan Charrington, Richard Bergman in California, that show that there's an indirect effect of insulin affecting glucose production. That is how it acts on the on the adipose tissue. Also, Mike Schwartz has said there's a role of insulin in the brain. And I tend to believe that those mechanisms are important in establishing a tone for the liver, how sensitive it will be to a prevailing stimulus. So I think they're all potentially important, but as you say, it's a big integrated response. And it's hard to identify any one mechanism as the single controller.
Okay, well, that's all very interesting. Now, what about if we think about where things can start going astray? So, you know, if you're not very active, so if you're inactive, there's a whole, dietary factors that you think about. It's very complicated. What can start going astray? And then we'll think a bit later about, can exercise help with that? So,
yeah, I mean, the first thing that comes to mind because of the public health problem of obesity is how an obese person responds to exercise. And barring any sort of musculoskeletal difficulties they have, orthopedic issues, obese people are capable of exercising without risking hypoglycemia or any other sort of acute disorder. And in fact, one thing that's an important line of protection, treatment for obesity or metabolic disorders is exercise, because it improves the sensitivity to insulin at not just in skeletal muscle, but also in the liver itself. So, and that helps prevent fatty liver from fats from accumulating in the liver. And work from John and Scott, John Tifo and Scott Rector have been very important in showing how exercise increases the oxidative capacity of the liver. And we've shown that after a single bout of exercise, there's an increase in insulin sensitivity. So I think in terms of, from a therapeutic standpoint, I think it can be an important mode of therapy for people who are with metabolic diseases or predisposed to metabolic diseases.
Absolutely. So can I just unpack that a little bit? So, we're talking about insulin resistance, a lack of insulin sensitivity, obesity, et cetera. So basically, with obesity, you get a situation where, the body is not responding to insulin properly. So the muscle is not taking up the glucose properly, and also the liver is not switching off properly, so it's pumping out glucose. So the glucose becomes elevated. And you're saying, that, and it's a very important point for people to know that during exercise, their glucose uptake is normal into the muscle, and and they get increases in insulin sensitivity. Yeah,
that's correct. So the fluxes, glucose production, glucose utilization may be dampened a little bit, but not enough to be a deterrent to exercise. Doesn't affect, it's not a limitation, and it's very close to normal, if not completely normal, depending on the subject. So I think exercise is a great opportunity for people to lose weight, improve their metabolic profile. Even if they don't lose weight, they're healthier. There's a redistribution of lipid stores, and the tissues have a greater oxidative capacity. So regular exercise with weight loss is a tremendous advantage, or is a great health benefit for people with obesity or metabolic diseases. But exercise, even if you don't lose weight, is of great benefit. And the big issue in our society, as it is in most industrialized society, is getting people to do it, getting people to comply with exercise programs. And so from that standpoint, people should find what they enjoy. And the key to tapping into the benefits of exercise is just doing it. So if you can get people to comply, it's a great health benefit for people with metabolic disease.
So an important point there you made, I just wanted to elaborate on a bit more, and just, I guess, put an exclamation mark after it, is that even you talk to medical doctors and they'll tend to think, yes, exercise is important because you lose weight, etc. But as you said, just one bout of exercise will increase your insulin sensitivity for 24 to 48 hours or so. And then, chronic exercise is even better as well. So is it fair to say that, because I've been more familiar with muscle, so, we always say acute bout of exercise will increase insulin sensitivity of the muscle for 24 to 48 hours. Is it about the same with the liver? Same sort of time?
I think so. The increased insulin sensitivity following exercise persists and will last well after the bout of exercise is over.
So the amazing thing is that, we tend to say to people, it'd be great if you exercise every day, but, a few days a week would be perfect. But it actually means you're getting that, if it's every 48 hours, then if it's lasting for 48 hours, you're actually keeping it sensitive the whole time. All right, so what else can go wrong in the liver, I guess? You can get fatty liver, you can get all sorts of, cirrhosis from smoking and whatever. Do we know anything much about whether exercise can sort of reverse these sort of things? So, if someone's already sort of down the track a little bit, do we know much about that? Can exercise turn that around?
Yeah, it seems, of course, exercise is good preventive medicine for fatty liver and metabolic diseases. Now, you can decrease fatty liver up to a certain point, but once the liver gets to the point where it's getting fibrotic, cirrhotic, and more extreme, it becomes more and more difficult and probably to reverse, and probably is not reversible after a certain point. So it's like many disorders, you want to catch it soon and act and begin an exercise program sooner rather than later.
It's probably making me think of the heart. It's probably the same thing. The heart, as it starts to deteriorate, you start getting heart failure, you start getting liver failure. If you start early enough, you can turn it around, you can slow it down. But after a certain point, you need a heart transplant, you need a liver transplant.
Right.
Yeah.
Well, I think one of the problems, I think there are people who have far more expertise than I do in this area, but once you get to a certain point, you start developing all these cross-linking proteins, and they have post-translational modifications that extend their half-life. And once a protein's cross-linked, it can be very hard to reverse that.
Yeah.
And they can be around for years.
All right, we'll probably start thinking about wrapping up. This has been great. One last thing I was thinking about was we're talking about all the complexity and the integration and things. You start thinking about crosstalk between organs. So, we always think about the muscle talking to other structures, such as, I said, IL-6 being released from the muscle, interacting with the liver. What's going on with the liver with crosstalk? Is the liver communicating, during exercise with other organs? Is the other organs talking to the liver? I know it's probably complex again, but.
Well, it is, there's a lot of unknown, untapped information, a lot to learn. So the liver is loaded with nerves. It's heavily innervated by the autonomic nervous system, parasympathetic and sympathetic. That's afferent and efferent. But also there are hepatokines. There are proteins and that are released from the liver. And I think that this is a whole domain that remains to be fully defined. In fact, I think maybe we've just scraped the surface. Mm-hmm. So there have been some terrific studies, some of which by Matthew Watt, one of your homies in Melbourne. Mm-hmm. And others who've shown that you have proteins that are secreted by the liver and they can increase during exercise. Now, what they do is the purpose of these hormones, whether they're just whether they have a physiological role within the context of exercise remains to be better elucidated. What I tell people, and I'm asked this all the time, just kidding, I'm rarely asked this, but every organ, you can assume that there's communication with between organs. And the kidney and the liver, the muscle, the liver, and it can be humoral or neural. And
so humeral's in the blood, yes, just to clarify.
Humoral would be a bloodborne signal.
Yeah.
And I think there's more that is unknown than is known right now. There's a lot to learn.
Okay, great. Right, one last thing I was just thinking, it was, you said if you have GLUT4 knockout, so that's the glucose transporter in the muscle, the main one for taking up glucose, and you exercise, you still get an elevation in glucose. What about, we did studies where we looked at carbohydrate ingestion during exercise, using like double traces. So we could see the glucose uptake by the muscle, but also the liver glucose output, and then how much glucose was coming from the gut. And we found that when you ingest carbohydrate during exercise, you do shut off, not fully, the liver. So that's interesting that it doesn't really happen though if you have the GLUT4, you don't really shut the liver off. Is that what you're saying?
Well, I think these are different situations, because when you ingest glucose, you're going to have an increase in insulin levels and all these things that act to squash the liver.
Exactly.
So the liver's, I talked before about how the liver can be a rechargeable battery. Well, you confuse it when you eat and exercise, and it's in the middle of recharging while it's also discharging. Now, the GLUT4 knockouts study glucose feedback in a different way, because it does it without having extra fuels coming in there. And in fact, it prevents the normal exercise-induced increase in glucose uptake. And you need GLUT4 to pick up glucose. So
very different. Yeah, so this is actually a nice little segue. We're going to have Louise Burke on in a few days, and she'll be talking about carbohydrate metabolism during exercise, and carbohydrate drinks and things like that.
She would be the expert.
All right, well, thank you very much. It's been great. It's probably got a bit complicated for some people, but I was loving it, so that's great. Thank you very much.
Well, it's been my pleasure, Glenn. Thank you very much for asking me to participate.
Okay, good on you. See you, mate. Bye-bye.